current source is an electronic circuit that delivers or absorbs an electric current which is independent of the voltage across it. A current source is the dual of a voltage source. The term constant current sink is sometimes used for sources fed from a negative voltage supply. Figure 1 showed the schematic symbol for an ideal current source, driving a resistor load. There are two types. An independent current source delivers a constant current. A dependent current source delivers a current which is proportional to some other voltage or current in the circuit. Background. In circuit theory, an ideal current source is a circuit element where the current through it is independent of the voltage across it. It is a mathematical model, which real devices can only approach in performance. If the current through an ideal current source can be specified independently of any other variable in a circuit, it is called an independent current source. Conversely, if the current through an ideal current source is determined by some other voltage or current in a circuit, it is called a dependent or controlled current source. Symbols for these sources are shown in Figure 2. The internal resistance of an ideal current source is infinite. An independent current source with zero current is identical to an ideal open circuit. The voltage across an ideal current source is completely determined by the circuit it is connected to. When connected to a short circuit, there is zero voltage and thus zero power delivered. When connected to a load resistance, the voltage across the source approaches infinity as the load resistance approaches infinity. Thus, an ideal current source, if such a thing existed in reality, could supply unlimited power and so would represent an unlimited source of energy. No physical current source is ideal. For example, no physical current source can operate when applied to an open circuit. There are two characteristics that define a current source in real life. One is its internal resistance and the other is its compliance voltage. The compliance voltage is the maximum voltage that the current source can supply to a load. Over a given load range, it is possible for some types of real current sources to exhibit nearly infinite internal resistance. However, when the current source reaches its compliance voltage, it abruptly stops being a current source. In circuit analysis, a current source having finite internal resistance is modeled by placing the value of that resistance across an ideal current source. However, this model is only useful when a current source is operating within its compliance voltage. Implementations passive current source equals, the simplest non-ideal current source consists of a voltage source in series with a resistor. The amount of current available from such a source is given by the ratio of the voltage across the voltage source to the resistance of the resistor. This value of current will only be delivered to a load with zero voltage drop across its terminals. The current delivered to a load with non-zero voltage across its terminals will always be different. It is given by the ratio of the voltage drop across the resistor to its resistance. For a nearly ideal current source, the value of the resistor should be very large, but this implies that, for a specified current, the voltage source must be very large. Thus, efficiency is low and it is usually impractical to construct a good current source this way. Nonetheless, it is often the case that such a circuit will provide adequate performance when the specified current and load resistance are small. For example, a 5V voltage source in series with a 4.7 kΩ resistor will provide an approximately constant current of 1 mA to a load resistance in the range of 50 to 450 ohm. A Van de Graaff generator is an example of such a high-voltage current source. It behaves as an almost constant current source because of its very high output voltage coupled with its very high output resistance, and so it supplies the same few microamperes at any output voltage up to hundreds of thousands of volts for large laboratory versions. Active current sources without negative feedback equals, in these circuits, the output current is not monitored and controlled by means of negative feedback. Current stable nonlinear implementation, they are implemented by active electronic components having current stable nonlinear output characteristic when driven by steady input quantity. These circuits behave as dynamic resistors, changing its present resistance to compensate current variations. For example, if the load increases its resistance, the transistor decreases its present output resistance to keep up a constant total resistance in the circuit. Active current sources have many important applications in electronic circuits. They are often used in place of ohmic resistors in analog integrated circuits to generate a current that depends slightly on the voltage across the load. The common emitter configuration driven by a constant input current or voltage and common source driven by a constant voltage naturally behave as current sources because the output's impedance of these devices is naturally high. The output part of the simple current mirror is an example of such a current source widely used in integrated circuits. The common base, common gate and common grid configurations can serve as constant current sources as well. A JFET can be made to act as a current source by tying its gate to its source. The current then flowing is the IDSS of the FET. These can be purchased with this connection already made, and in this case the devices are called current regulator diodes or constant current diodes or current limiting diodes. An enhancement mode N-channel MOSFET can be used in the circuits listed below. Following voltage implementation, an example, bootstrapped current source. Voltage compensation implementation. The simple resistor current source will become ideal if the voltage across the load is somehow held zero. This idea seems paradoxical since real loads always create voltage drops across themselves, but it is yet implemented by applying a parallel negative feedback. In these circuits, an op-amp compensates the voltage drop across the load by adding the same voltage to the exciting input voltage. As a result, the op-amp inverting input is held at virtual ground, and the combination of the input voltage source, the resistor and the supplied op-amp constitutes an ideal current source with value IOUT equals VAN/R. The op-amp voltage to current converter in Figure 3, a transimpedance amplifier and an op-amp inverting amplifier are typical implementations of this idea. The floating load is a serious disadvantage of this circuit solution. Current compensation implementation, a typical example a Howland current source and its derivative Deboo integrator. In the last example, the Howland current source consists of an input voltage source VAN, a positive resistor R, a load and a negative impedance converter INIC. The input voltage source and the resistor constitute an imperfect current source passing current IR through the load. The INIC acts as a second current source passing helping current IR through the load. As a result, the total current flowing through the load is constant and the circuit impedance seen by the input source is increased. However, the Howland current source isn't widely used because it requires the four resistors to be perfectly matched, and its impedance drops at high frequencies. The grounded load is an advantage of this circuit solution. Current sources with negative feedback equals, they are implemented as a voltage follower with series negative feedback driven by a constant input voltage source. The voltage follower is loaded by a constant resistor acting as a simple current-to-voltage converter connected in the feedback loop. The external load of this current source is connected somewhere in the path of the current supplying the current-sensing resistor but out of the feedback loop. The voltage follower adjusts its output current IOUT flowing through the load so that to make the voltage drop VR equals IOT R across the current sensing resistor R equal to the constant input voltage VAN. Thus the voltage stabilizer keeps up a constant voltage drop across a constant resistor. So, a constant current IOUT equals VRR equals VAN flows through the resistor and respectively through the load. If the input voltage varies, this arrangement will act as a voltage-to-current converter. It can be thought as a reversed current-to-voltage converter. The resistance determines the transfer ratio. Current sources implemented as circuits with series negative feedback have the disadvantage that the voltage drop across the current-sensing resistor decreases the maximal voltage across the load. Simple transistor current sources equals constant current diode equals. The simplest constant current source or sink is formed from one component, a JFET with its gate attached to its source. Once the drain source voltage reaches a certain minimum value, the JFET enters saturation where current is approximately constant. This configuration is known as a constant current diode, as it behaves much like a dual to the constant voltage diode used in simple voltage sources. Due to the large variability in saturation current of JFETs, it is common to also include a source resistor which allows the current to be tuned down to a desired value. equals Zener diode current source equals. In this bipolar junction transistor implementation of the general idea above, a Zener voltage stabilizer drives an emitter follower loaded by a constant emitter resistor sensing the load current. The external load of this current source is connected to the collector so that almost the same current flows through it and the emitter resistor. The transistor Q1 adjusts the output current so as to keep the voltage drop across the constant emitter resistor O2 almost equal to the relatively constant voltage drop across the Zener diode DZ1. As a result, the output current is almost constant even if the load resistance and or voltage vary. The operation of the circuit is considered in details below. A Zener diode, when reverse biased, has a constant voltage drop across it irrespective of the current flowing through it. Thus, as long as the Zener current is above a certain level, the voltage across the Zener diode will be constant. Resistor R1 supplies the Zener current and the base current of NPN transistor. The constant Zener voltage is applied across the base of Q1 and emitter resistor R2. Voltage across R2 is given by Vz, VBE, where VBE is the base emitter drop of Q1. The emitter current of Q1, which is also the current through R2, is given by. Since Vz is constant and VBE is also constant for a given temperature, it follows that VR2 is constant and hence IE is also constant. Due to transistor action, emitter current IE is very nearly equal to the collector current IC of the transistor. Thus, the load current is constant and the circuit operates as a constant current source. As long as the temperature remains constant, the load current will be independent of the supply voltage, R1, and the transistor's gain. R2 allows the load current to be set at any desirable value and is calculated by or, since VBE is typically 0.65 V for a silicon device. IR2 is also the emitter current and is assumed to be the same as the collector or required load current, provided HV is sufficiently large. Resistance R1 at resistor R1 is calculated as where K equals 1.2 to 2. And HV, min, is the lowest acceptable current gain for the particular transistor type being used. Equals LED current source equals. The Zener diode can be replaced by any other diode, for example a light-emitting diode LED1 is shown in Figure 5. The LED voltage drop is now used to derive the constant voltage and also has the additional advantage of tracking VBE changes due to temperature. R2 is calculated as and R1 as, where ID is the LED current. Equals transistor current source with diode compensation equals. Temperature changes will change the output current delivered by the circuit of Figure 4 because VBE is sensitive to temperature. Temperature dependence can be compensated using the circuit of Figure 6 that includes a standard diode D in series with the Zener diode as shown in the image on the left. The diode drop tracks the VBE changes due to temperature and thus significantly counteracts temperature dependence of the CCS. Resistance R2 is now calculated as. Since VD equals VBE equals 0.65 V. In practice VD is never exactly equal to VBE and hence it only suppresses the change in VBE rather than nulling it out. R1 is calculated as. This method is most effective for Zener diodes rated at 5.6 V or more. For breakdown diodes of less than 5.6 V, the compensating diode is usually not required because the breakdown mechanism is not as temperature dependent as it is in breakdown diodes above this voltage. Equals current mirror with emitter degeneration equals, series negative feedback is also used in the two-transistor current mirror with emitter degeneration. Negative feedback is a basic feature in some current mirrors using multiple transistors, such as the Widler current source and the Wilson current source. Equals constant current source with thermal compensation equals. One limitation with the circuits in Figures 5 and 6 is that the thermal compensation is imperfect. In bipolar transistors, as the junction temperature increases the VBE drop decreases. In the two previous circuits, a decrease in VBE will cause an increase in voltage across the emitter resistor, which in turn will cause an increase in collector current drawn through the load. The end result is that the amount of constant current supplied is at least somewhat dependent on temperature. This effect is mitigated to a large extent, but not completely, by corresponding voltage drops for the diode D1 in Figure 6, and the LED1 in Figure 5. If the power dissipation in the active device of the CCS is not small and or insufficient emitter degeneration is used, this can become a non-trivial issue. Imagine in Figure 5, at power up, that the LED has 1 V across it driving the base of the transistor. At room temperature there is about 0.6 V drop across the VBE junction and hence 0.4 V across the emitter resistor, giving an approximate collector current of 0.4 per reamps. Now imagine that the power dissipation in the transistor causes it to heat up. This causes the VBE drop to, say, 0.2 V. Now the voltage across the emitter resistor is 0.8 V, twice what it was before the warm-up. This means that the collector current is now twice the design value. This is an extreme example of course, but serves to illustrate the issue. The circuit to the left overcomes the thermal problem. To see how the circuit works, assume the voltage has just been applied at V+. Current runs through a 1 to the base of Q1, turning it on and causing current to begin to flow through the load into the collector of Q1. This same load current then flows out of Q1's emitter and consequently through our sense to ground. When this current through our sense to ground is sufficient to cause a voltage drop that is equal to the VBE drop of Q2, Q2 begins to turn on. As Q2 turns on it pulls more current through its collector resistor R1, which diverts some of the injected current in the base of Q1, causing Q1 to conduct less current through the load. This creates a negative feedback loop within the circuit, which keeps the voltage at Q1's emitter almost exactly equal to the VBE drop of Q2. Since Q2 is dissipating very little power compared to Q1, Q2 will not heat up any significant amount and the reference voltage across our sense will remain rock steady at 0.6 V, or 1 diode drop above ground, regardless of the thermal changes in the VBE drop of Q1. The circuit is still sensitive to changes in the ambient temperature in which the device operates as the BE voltage drop in Q2 varies slightly with temperature. Op-amp current sources. The simple transistor current source from Figure 4 can be improved by inserting the base emitter junction of the transistor in the feedback loop of an op-amp. Now the op-amp increases its output voltage to compensate for the VBE drop. The circuit is actually a buffered non-inverting amplifier driven by a constant input voltage. It keeps up this constant voltage across the constant sense resistor. As a result, the current flowing through the load is constant as well. It is exactly the Zener voltage divided by the sense resistor. The load can be connected either in the emitter or in the collector, but in both the cases it is floating as in all the circuits above. The transistor is not needed if the required current doesn't exceed the sourcing ability of the op-amp. The article on current mirror discusses another example of these so-called gain-boosted current mirrors. Voltage regulator current sources. The general negative feedback arrangement can be implemented by an IC voltage regulator. As with the bare emitter follower and the precise op-amp follower above, it keeps up a constant voltage drop across a constant resistor. So, a constant current flows through the resistor and the load. The LED is on when the voltage across the load exceeds 1.8 V. The grounded load is an important advantage of this solution. Kerpistor tubes, nitrogen-filled glass tubes with 2 electrodes and a calibrated Becquerel amount of 226 Ra offer a constant number of charge carriers per second for conduction, which determines the maximum current the tube can pass over a voltage range from 25 to 500 V. Current and voltage source comparison. Most sources of electrical energy are best modeled as voltage sources. Such sources provide constant voltage, which means that as long as the current drawn from the source is within the source's capabilities, its output voltage stays constant. An ideal voltage source provides no energy when it is loaded by an open circuit, but approaches infinite power and current when the load resistance approaches zero. Such a theoretical device would have a 0 ohm output impedance in series with the source. A real-world voltage source has a very low, but non-zero output impedance, often much less than 1 ohm. Conversely, a current source provides a constant current, as long as the load connected to the source terminals has sufficiently low impedance. An ideal current source would provide no energy to a short circuit and approach infinite energy and voltage as the load resistance approaches infinity. An ideal current source has an infinite output impedance in parallel with the source. A real-world current source has a very high, but finite output impedance. In the case of transistor current sources, impedances of a few megohms are typical. An ideal current source cannot be connected to an ideal open circuit because this would create the paradox of running a constant, non-zero current through an element with a defined zero current. Also, a current source should not be connected to another current source if their currents differ, but this arrangement is frequently used. Similarly, an ideal voltage source cannot be connected to an ideal short circuit, since this would result a similar paradox of finite non-zero voltage across an element with defined zero voltage. Also, a voltage source should not be connected to another voltage source if their voltages differ, but again this arrangement is frequently used. Contrary, current and voltage sources can be connected to each other without any problems, and this technique is widely used in circuitry. Because no ideal sources of either variety exist, any current source can be considered as a voltage source with the same source impedance and vice versa. These concepts are dealt with by Norton's and the copyright Venin's theorems. See also, constant current, current limiting, current loop, current mirror, current sources and sinks, Fontana bridge, a compensated current source, iron-hydrogen resistor, voltage to current converter, welding power supply, a device used for arc welding, many of which are designed as constant current devices. Widler current source. References and notes. Further reading, Current Sources and Voltage References Lyndon T. Harrison. Pub. Elsevier Nunes 2005. 608 pages. ISBN 0-7506-7752-X. External links, tutorial video on how to build a constant current source using an Lumen 317, current regulators. Electrical Engineering Training Series, 4QDTEC, Electronics Circuits Reference Archive, Differential Amplifiers and Current Sources, article about current sources on ESP.